so if you're interested, definitely consider going. And I guess unless there are other important announcements, I'm not really seeing anything. So Jeff, feel free to go ahead and get started.
Well, thanks for having me here. The meeting is small, but hey, it's intimate that way, right? I'm coming here, I guess, from the University of Lowbrow Astronomers, and I suspect, like you guys, we're strictly an amateur club. We're loosely affiliated with the university, but we're not actually tied to a university department. So we're a little bit more informal, which kind of goes along with that whole lowbrow thing. For historical reasons and some bad attitudes way back in the 80s or 70s, our group got labeled the lowbrows because we weren't scientific enough. So it's basically a bunch of folks that like to look at the night skies and whatnot. I also hold a position with the Great Lakes Association of Astronomy Clubs, which is kind of an umbrella organization for 10 clubs around the southeastern Michigan area. And as you see from my sweater, I work for UMITS, so I'm alumni, staff, you name it, and I got Michigan stuff all over the place. And I also play saxophone for about 4 bands, which is probably way too much. I'm going to have, I gave Kimberly a URL that she can share for the presentation, so you don't really have to take notes for anything that's on the slides anyway. I kind of went in a little bit about the lowbrows here. We do hold open house events under normal circumstances, non-COVID pandemic. We were doing them basically once a month through April through October. It looks like this year we're going to do those again. It's on the Peach Mountain site in Dexter, which is the site of a very large, I think it's like a 65-foot radio telescope, which we have nothing to do with, but there's Professor Cutler at the College of Engineering. He runs that. We have a smaller installation with a 24-inch Cassegrain telescope. And our meetings are usually the third Friday of the month, which happens to be tomorrow. In G115 Angel, and you're all welcome to come. It's in person, or if you don't feel comfortable doing that with university rules, here's the Zoom URL with our passcode, which is all lowercase. This font didn't really show that, and of course our URL for the website. Our other shameless promotion is for the GLAC organization, and I said, it's 10-member clubs. We have donations that we take, 501c3. So they're all tax-free and that kind of thing. Our big thing is we hold an Astronomy at the Beach event, which is at Island Lake State Park in September. And this year it's going to be on the 16th and 17th. It amounts to when the moon is about a half moon. So if they can see the moon and all of its splendor, as well as some of the dark sky objects that are out there. So it's a nice date. And information on the event will be at that URL there. So. And lastly, my little spiel, if you will. Oh my God, I forgot to share.
Okay, I got you.
You got me, share. Good.
Everything's all fine.
Well, let's go to the beginning of the thing just to give. Yeah, I can't believe I did that. There. That's so unprofessional. Ta-da! Sorry about that. I was all worried about getting a smooth entry and forgot all about sharing. And like I say, Kimberly will have all of this stuff emailed to you guys anyway. So a little bit of that going on. There we go. My little thing is like I started out with my astronomy with this orange telescope here. And I call it the orange can. So naturally, if you're doing astronomy with the orange can, it's the orange can astronomy. And I have a Facebook page that basically has trials, tribulations, and lots of photographs of the stuff that I've taken. This is kind of the latest setup. I've got a couple other smaller telescopes to go along with it that have got, different images and whatnot. So with that, what are we going to cover? Oh my God, I kind of went into this and it's like the range of topics is pretty broad. And so I kind of decided on, what are the kinds of things you're going to see, what equipment we're going to do, and maybe some of the techniques after the fact for, getting spectacular images. So that's kind of the gist of what it is. And we'll just start out right with the stuff that you're going to see in the sky. We usually group things between two categories: planetary, which is generally everything within the solar system and pretty close. And they're all relatively bright, they're close by, and a lot of them you can see with your naked eye without any help. And those that are, a little tougher, binoculars or even a smallest telescope can do that for you. Notable objects is, well, the sun, of course. And I should note that this picture here is the only one that is not one that I've taken. I didn't have a good whole disk image of the sun. These are actually two different types of telescope filters that are on here. This one is an H alpha, which gives you this flare detail that's there, as well as this one, which is a normal visible light, and that gives you the sunspots and some of that. You notice there's a lot less detail with this one than there is with that. Of course, the moon. This image was actually, it was taken in two halves and spliced together, which we'll get into a little bit later. And all the planets that we can see real easily, which amounts to Mars. Mars is actually a trickier one to photograph because it has an atmosphere that we can, we have to look through, and it's small enough where the atmosphere gives us troubles photographing it. Of course, Jupiter and Saturn, which are very bright and easy to photograph, and even easier to bring out all kinds of colors and details and the stripes and whatnot that are on the surface, the cloud surfaces and stuff. This particular photo, I managed to get 3 of the Galilean satellites, which was pretty special. Next out is Uranus and Neptune, which you technically can't see with your eye. I think they're too dim, but with a telescope, these were taken, I believe, around 15 to 20 seconds of exposure time. But you need a tracking telescope, things like that, to find them. You notice Uranus is, Uranus is closer, so it's a little bit brighter. And then, of course, Neptune is further away. You get a little bit more of the sense of a disk here, and a little less so with Neptune. The next category was what we call deep space objects, or DSOs. These are stuff that is outside of our solar system. It tends to be very, very far away and very dim. Some of the closest things are, a matter of like 10, 12 light years away. So they're generally outside. And you can technically see the core, the bright core of a lot of these things with your naked eye, but they're going to be more difficult. The kinds of objects that we have are going to end up. Actually, Kimberly, are you running this presentation? Because I could share my screen just as easily.
Yeah, I was running it for now, but if you want to switch over.
Why don't we do that? Because you won't. It'll be harder to see the. Presentation that way. Let's do that. Sorry for my mess up, folks.
Oh, no problem.
So let's move this window out of the way. Here we go. So what we got here, these are star clusters, which are basically billions of objects. And, come on. Continue. And I'm an IT guy, and I don't know why this is giving me problems. There we go. Now we're back on track. Sorry about that. So star clusters are literally billions of stars all located in the same place. This little guy over here is what they call an open cluster. You can see it's very loosely associated, if at all. Sometimes open clusters are just dense areas. And then these are a lot tighter clusters here. This is M5, which is a Messier object. And I forget which one this one came from. I bet it's M10 or 12. Those are references to star catalogs, by the way. The other things that we can see is nebulas, which are basically clouds of gas. They're lit either from behind or from the front from neighboring stars. Things like the Omega cluster, or like this is a nebula, it's a planetary nebula because it looks kind of like a planet in the sky. This one technically is that way. These are just gas clouds here. And then this one you can see is a very thin, wispy object called the Veil Nebula, and this is one portion of it. Its size is larger in the screen in the sky than what my telescopes can capture. So usually people get them in composite or mosaic photos. This is one I'm particularly proud of, the Orion Nebula, sorry, and it was taken with a $250 telescope. So mounts and cameras are a bit more, but it was one of my better photos, and it was nice to show it off here. So you see some of the different cloud layers, and the internal stars here are usually they wash out everything, but I managed to get it just right. Got a little bit of dust lanes in front. It was a nice photo, actually. And lastly, galaxies. These are billions, if not billions and billions. It's the star Carl Sagan thing. And some of them are very small, so you can zoom in on them and see just that object. Other ones you can catch 3 or 4 in one field of view. This one up here is the Milky Way, or the Andromeda Galaxy, which are our closest galaxy to us. And the photo here isn't really great, but it does show the dust lanes that are in front, which obscure what the central object is. So those are the kinds of things you'll be seeing if you look out of a telescope. So that's what the guys are all interested in the club. These types of telescopes here, basically I want to just run through the quick things. They all have different characteristics and whatnot, and there's basically 3 different kinds. This difference between these two, they're both Cassegrain telescopes. Okay, don't touch your mouse too much, Jeff. Cassegrain meaning kind of a mix of reflecting and refracting telescopes. But before I get ahead of myself, the first one is what they call a refractor, and this is the classical telescope that everybody thinks of, where you have a big objective lens on this side, and you bring to focus on an eyepiece that you can look out of, and it's basic magnifying glass material here. Usually if you have a camera, that's going to be positioned very precisely about where your eyeball would be, and because of the mechanics and some of the attachments and all that, that's sometimes a little more difficult than we originally think. So you often have to change focuses and things when you attach cameras, which apply to all telescopes. And these are some of the examples of those that will probably look very familiar to you. And they can come in, ultra cheap ones, which you can get one of these things for probably $100 or something. And this one is probably going to go for about 4,000 or 5,000 these days. And the sizes are roughly the same, which are both very small. Refractors usually top out around 120, 150 millimeters because the glass is very expensive and hard to manufacture once you get to those larger sizes. There's always pros and cons to any of these designs, and this is where if they're going to buy a telescope, you have to kind of pay attention to what they're doing and what you want to look at. The pros, obviously, these things are rugged. Everything is fixed in place. There isn't anything to really adjust or maintain on them. They're really good at that. The short tube model, like the one on the right here, those are good because they offer a wide field of view, just like you might have a camera lens. With the shorter the camera lens, the wider field of view you're going to have. And of course, with those, you usually get very fast focal ratios. So the fast focal ratios will affect how sensitive of your camera or your film will have to be. The downside is they tend to be found on the small side. They tend to be very heavy, and the price goes up dramatically the nicer or the more aperture, the opening that you get, and the better glasses. So that chromatic aberration is mentioned here. It's where it does a color distortion. And if you want to eliminate that, or you don't feel like doing that in your post-processing, then you'll buy better glass, which that's when you get into those thousands mark. The next type is is a Newtonian reflector. It's a classical design that Newton used, obviously, and it uses basically this is where the light is coming in from this side, and it uses a big mirror here to focus it on a secondary mirror and out to your eyepiece. These tend to be very fast focal ratios because there's virtually no glass that slows down any of the photons that are coming your way. And they typically are very big and bulky because, hey, mirrors are cheap and easy to manufacture. So like this one is a smaller, probably like a 150 or a 200 millimeter, whereas this thing might be 18 inches, and they come as big as 24, 30 inches. How much do you want to pay after that? They still get expensive quick, but the bigger the aperture, the more stuff you're going to see, the dimmer objects that you're going to see. The downside is you can see they're pretty bulky. They are high maintenance because those secondary mirrors have to be aligned just so. And they're somewhat delicate because that adjustment and everything's just mounted to be as light and as vibration free as possible. But they tend to be very inexpensive because mirrors are easy to produce. Obviously, they're time tested just like the refractors are because they've been used for thousands of years or hundreds of years anyway. They have very good fast focal ratios, so you'll get good photos off of that. And they're, like I said, the apertures run really big. The last one is kind of a hybrid between the two because it uses a lens in the front here, and then they have a mirror in the back and another secondary mirror up here, and that shoots the light to the back side through a hole in the mirror back here to your eyepiece. So it's a very indirect way, but it's a way to basically get a very long focal length, which is good for like planets and the moon, things like that, to get that long focal length, but have it in a very compact package. And it's relatively light. The lenses are easy to grind compared to refractors. And they tend to look like this. The orange can that I have is a prime example of a Schmidt-Cassegrain. And they come in sizes maybe up to about 14, 15 inches, something like that. And they get expensive fast. The second design is kind of Cassegrain is a variation of that, where it used a curved lens here and another curved lens here. The light path is about the same, but because you get a smaller obstruction in here, you get a little more light coming through these. And because there's only one lens that they have to grind, and it's somewhat less complicated, it's a little cheaper to do. But they only go up to maybe 7-8 inches tops. The glass gets fragile, but you can see this curved lens in the middle here with the reflective coating in the back. And of course, all the Cassegrains, I probably went through most of these, plus pros and cons here. The mounts tend to get expensive on these because they're carrying usually anywhere from 10 to 12 pounds up to, I had a 12-inch scope that was close to 50 pounds. So you need a mount that's going to carry that weight, plus motors that are able to turn that weight and track everything. But they have good balance characteristics, etc. So there are some good trade-offs. And of course, it's what are you going to look at? They're great for planetary stuff, not so good for DSOs because they have a very narrow field of view. And I kind of touched on this earlier, but there's two different kinds of mounts as well. The standard for the Schmidt-Cassegrain, for instance, the lowest price one is the Next Star line from Celestron, which is a single arm. It has just a motor there and a motor in the base that will do the two motions you need necessary. Variation on that is the two fork design like this, and then Ioptron makes this AZ Mount Pro, which uses a counterweight and it puts everything on one axis. And that has some advantages because aside from your cameras running into the tripod, you don't have to worry about cameras and other things hitting this base and limiting what you can see in the sky. So Ioptron kind of did a nice job with that. The other kind of mount, I didn't really explain these will work in two ranges of motion, two axes. The base goes along like you would a normal camera mount, and then the up and down portion for the telescope. The second kind of mount works in basically the same way, but as you see here, the nice green arrow that I found this photo on, these are aligned with the pole of the Earth. It's a magnetic pole, or it's polar aligned, and that way you're spinning at the very same direction and angle that the Earth is spinning. And these you have to set for wherever you are in your latitude. So there's a little bit more to the alignment initially. You can't just set it down and go. But the advantage is that once you get tracking an object, you only have this single motor in this direction down here that has to turn. It'll just sweep through the entire sky all night. And so they have some advantages, and because it's only one motor, you get a lot smoother operation, and the astrophotographers love them for that. And they really are the best solutions. The altitude azimuth mounts, the other one, they're good for about 30 to 40 seconds of exposure before you start getting smearing. Whereas these guys here, it's pretty much sky's the limit. I know guys have taken up to 10, 20 minutes on these things. And then it's the quality of your mount that determines how good you're going to go. I probably gone through most of this stuff. The equatorial does have this nice thing called a meridian flip, which, because of the counterweight that you need to balance the scope, it ends up hitting the tripod roughly when things are directly overhead. So the scope is, all the manufacturers have made it so they basically flip sides. And so it takes about a minute for your telescope to realign itself and get itself back in. Obviously, the Alta-Z mounts are cheaper because they can be built very lightweight. They're not as high tech, all that kind of stuff. But yeah, it looks like I went through most of them. And the equatorial, you can get cheap ones, but they're wobbly and they're not very stable. So generally, around $1,000 is what they cost to get started. And I mean, $100 you can get an Alta-Z mount. But those are kind of the basic tools that we use to look at anything with any precision. And this same tools can be used whether you're doing strictly visual observing or if you're doing astrophotography. The visual observing is nice because you can basically set it on the object, let it slew, and you can have people come to your telescope all night, like we do at Astronomy at the Beach, shameless plug, and have them look at the same object for a long period of time, or until it hits trees or the horizon. And I tend to go into astrophotography, so there has to be this discussion about cameras. This is where, visual observing, once you get your telescope, you're done. If you want to go into astrophotography, there's a few more things involved. And that's why I figured I'd put it in. Incidentally, this type of camera is not acceptable. I have to imagine somebody might have guessed that, but I have to put it out explicitly. The two big types of cameras are what the DLSR that everyone's familiar with. You take land type photos, you take family photos, etc. with the things, and most of them these days have got very good sensors in them. They tend to be fairly big sensors, which is great because you can fit a wide field of view with your photos. And they also have highly adjustable sensitivity, like the ISO settings or your f-stops and whatnot, to change how you're going to take that picture. And those are all important things. The other type of camera is basically it's a CMOS or a CCD type camera. CMOS is the newest technology. They're kind of taking off because they're probably a third of the price. All of my cameras are this is the ZWO brand. They're all these red canisters. They look like little hockey pucks. They're kind of fun. They have fewer settings, but because of the nature of the cameras, they don't need all those adjustments. So they tend to be a little cheaper initially going to here, but you can also spend a lot of money on a really good sensor and to really kind of dial it in. My two CMOS camera, or actually three, they are specifically, I bought them because the resolution of the chip matches the resolution of my telescope. So there was no point in getting a super high resolution camera if my telescope is only going to do so much resolution. So matching those two up can actually help you out quite a bit in post-processing times. There's a lot of differences between the two. I mentioned the pixel size. You get a big sensor with a DLSR, but it also doesn't have any consideration for the thermal noise that happens. So if you have a long exposure of, say, 2 or 3 minutes and all that, that sensor is going to heat up, and in doing so, it's going to produce bad pixels, or hot pixels they call them, due to the thermal difference. When you get into a dark camera on the CMOS side, they come with built-in coolers that can, like mine, will go down to -30 Celsius. And it's amazing the difference just going down to, say, -10 Celsius. You get rid of all sorts of noise instantly without any post-processing or special dark frames or other techniques that you can use. The nice thing about the DLSRs is that you can use them for your family photos or just about anything needed. And most everything that you need to take pictures of astronomy, say, the Milky Way or something wide sky, is on the camera itself. So there's no other junk to carry around. Get your tripod, usually a tracking tripod, and you set it down and take pictures. We have one guy in the club that he's a wide field guide, and he comes out, he goes all over the place. He sets up in a couple of minutes, and he's off and taking pictures. My setup is a little more involved, but I don't do wide sky, and it takes me about a half an hour on a good day. There's some other technical things that are better about CCD cameras, or CMOS, either way. Like I say, the thermal stuff. This H alpha is it's good at seeing the very low temperature hydrogen gases that are around nebulas and whatnot. So they tend to be very good for and they require a laptop, and like everything else, they come in a wide variety of prices. When we're doing astrophotography, the big thing, the very first thing you're going to do is you get all your junk set up, and you tie it to your laptop, or you have a built-in computer that is plugged into the thing. But all these CMOS cameras run off of a USB cable. And so you have some kind of setup, and there's a capture software that's going to run. And if, say, you're taking a planetary, because the planets move so fast, which sounds crazy because they move in 3 minutes, you can detect movement on Jupiter or Saturn. So exposure time, the sensitivity, those are your two big factors in the CMOS cameras. And sometimes you might want to do, say, a video file and then process it, or do a series of stills that are maybe, say, 2 minutes each long. And the more data you collect, the whole idea is to get your signal to noise ratio up so that you gather more of the good stuff and leave the light pollution and all the other noise from the camera and other things behind. If you're capturing, of course, you want this metadata. That'll tell you about what settings, what temperatures, all that kind of stuff that was used when your camera was capturing this stuff. And it's useful because you usually have to mate up those there's a technique using what they call dark frames, which you basically take a picture of nothing but a dark spot, and whatever the camera might have some defective pixels and all that, that'll pick it up, so that later in your post-processing you can subtract that dark frame out of there. And so you have to take them at the same temperature and resolution and all that nonsense. So having that metadata is helpful in getting that stuff out. The capture software is, of course, it keeps all your files nice and collected in single directories or whatever. And then kind of the planning, because you're out there, and you, like in the summer, you might only have 4 or 5 hours, well, maybe 5 or 6 hours here of daylight or darkness out there that's usable. So you want to make good use of your time. So a lot of the software has got very automated lately, so that you can literally say, okay, I'm going to take 50 frames of this at this exposure and gain, and then I'm going to take a couple of darks, and then I'm going to switch targets to this over here, and the software can do all of that. Some guys who have observatories, they open up the observatory, punch run, and then they go to bed. Likewise, I am not one of those people. I have to set up my stuff and take it down. So in the winter, astrophotography is pretty challenging from a thermal standpoint, i.e. I freeze my butt off. The nice thing about all this is that you can, all the software and all that is like in just about every category, there are a number of free options that are very good. And even like some of these licensed software that I've got here, yeah, they cost money and all that, but they don't do any better job than the freebies. The free software on the left, SharpCap and FireCapture are the two competent ones these days. OpenCapture is a little old these days. But both those are free, and they're both excellent packages. And even the people who are using more sophisticated software later in the chain, they will still use SharpCap or FireCapture to get their initial captures because it's such a good tool. It's a very focused tool, and they're free. I mean, the price cannot be beat. The next thing to do once you've got this collection of images is that you're going to, of course, align them. So if you've got stars and your capturing has changed, you want to make sure that everything matches up so you get nice sharp images. And the software can do all of that. It has, often they have maps, star maps that are built in so it knows, where it needs to do, how much it needs to rotate, all that kind of stuff. All of them will analyze the photos, determines like, is this a real noisy photo? Is it got a lot of does it have some skips in it? Did a satellite come rushing through, like one of those Elon Musk Starlink satellites, or the space station, for instance? That's one of those things people capture, and the software will pick out those frames and say, okay, those are not good. And usually once you get your stack of quality images, or stack your pile of images, you're going to stack them together, and what that'll do is basically add them up. And so once they've been aligned, you have good quality images, you'll add them up, and that will, like maybe a cloud went by, or, even a cloud, and I say it's very wispy, and it could dim an image and obscure some detail in Jupiter. Or if the sky is unsteady, and you've seen that thing on a highway, a hot highway, where you get kind of the shimmery effect. It happens all the time in the atmosphere, and so what you capture in one instant might not be what you see in the next instant. So by taking lots of images, you can minimize that effect. And by stacking them, you basically can add up all the good stuff. Say, maybe on one frame out of the 100 you collected, you found this, spot on Jupiter and didn't appear anywhere else. Well, by stacking, you get that in there as well as all the other detail. So this is kind of like a Christmas present situation. So you collect a whole bunch of images, you spend hours doing it, you freeze your butt off at night, and then the next day you come sorting through gigabytes of images, and it's like, well, each individual image, it looks okay, and I can tell that it's Jupiter or some nebula, sometimes not. Okay, I think this might be a good image, but after you stack, that's when you find out how good all of your collection was and how good your processes were, all that kind of thing. And it's astounding. I mean, it just bowled me over the first time I did it, in seeing all of this detail from Jupiter just pop out at me. It's like, I looked through the eyepiece, I didn't see any of that. I looked through my camera, at a single frame, and I didn't see any of that. But when you do the alignment and stacking phase, then just things pop out at you, and it's simply amazing. And the same techniques go for deep sky DSO images versus planetary. They all have to go through that. And of course, like everything else, there's a number of alignment and stacking programs. Frankly, the AutoStacker 3 and Registax, that combination, neither one does 100% job. So together, the tools are fantastic, and they do amazing work for planetary, and just about everybody uses those two to get to their final stage. Nebulosity does an okay job. Some people get really good results with it. I haven't been able to go there. And then for deep sky stuff, that usually requires a lot more intelligence as far as the alignment and all that, because you're talking about such expanded times. Taking a a 50 millisecond image of, say, Jupiter, and you do a video of a couple thousand images in 3 minutes, that's going to be a lot different process than taking, say, 30 or 45-minute images of some obscure nebula. And so these packages, they have to deal with a lot more rotation of the Earth, changes in the sky, etc. And so they tend to be more expensive. There is a freebie, Deep Sky Stacker, and it does a fabulous job in most cases. I managed to find a case that it did not work, and I bought that AstroPixel processor APP next, and it's fantastic. If you're really a hard case and maybe you're really good at Photoshop or GIMP, there's another program called PixInsight that it's like a collection of astronomy tools, and it can do everything, but why would you want to do it? It's painful, just painful. The learning curve is incredible. But if you like pain, those last three are probably good for doing your alignment and stacking. Highly not recommended. Let the programs do their work. They're very focused and good at it. I wanted to show you this image because it's the image on the left was done with DSS, and this is M27, the Dumbbell Nebula. And you can see the Dumbbell Nebula actually sits up almost near the pole at the very top of the sky. And you can see, and this was taken with an Alt-AZ mount, so it was kind of a non-optimal mount for that particular object, but because it's straight up, it really was only running on one motor anyway. But because the sky is rotating so much faster up there and it was harder for the mount to keep up, you can see that we got a lot of like star spots here and streaking, oval stars and whatnot. And it did get the object. The object itself is not too bad. But all this streaking just made a complete mess of the background. And so I was kind of bummed. I tried all kinds of different ways of doing it. And then I bought APP because it said it was doing mosaics. And I was thinking the mosaic, they can deal with rotation well. That was my thought. And indeed, that was right. But it turned out a little different than I thought. And you can see how much each individual frame was stacked. And you can see how much the image actually rotated during that time, which I think was only about an hour's worth. But with that same mount, the same base frames, all the captures were done a single. This wasn't a different night or anything. That same data went through this program and it produced this image. And I showed the lowbrows that, and they were simply astounded that I managed to capture it that well and on that kind of mount, because that wasn't an equatorial mount. It's like, no. So they were impressed, and that part of that's a personal thing because I like pushing envelopes and pushing the equipment as far as I can. And this is one of those times where I push the software further into it than I could get with my cameras. But it's a nice one to show off that kind of thing. And the last step is like once you got this marvelous stacked image and all that, you often want to clean it up and make it look that close to Hubble as you can. And given, and say, an 8-inch telescope or even my 120 is like you're never going to get Hubble, but it's the standard we shoot for. Things that you can change. Obviously things: the contrast, the brightness, the sharpness. The wavelets feature. This is actually specific to Registax. They have a thing called wavelets, and it's basically dealing with sharpness, but dealing with, say, like the first level, it deals with, say, a 10 pixel square, and it tries to get the most sharpness out of the 10 pixels and across your entire image. And then you can adjust it a couple of different ways there, and then you go to the next level, and then within that 10, it'll chop those into, say, 5 pixel segments and work on sharpness within there. And by going through the process, by the time you've gone down to 4 or 5 levels, you're bringing out single pixel details that were never there before. And this is the last step it just drops your jaw, because you're seeing this image pop out at you. And it's like, that didn't show up in the raw image. It didn't show up in my stacked image. But all of a sudden, I've got this marvelous set of detail, and it's like a Christmas present. It really is. So there's a lot of personal gratification in doing that. And obviously, color adjustments. So if you get the sky tends to be very blue, and you can adjust the blue down, and or if you capture a nebula, you might get a ton of red, so you can back that off and make it look pleasing to the eye. No matter what anybody says, there are no true colors to the sky, the objects in the sky. They are all artistic representations by whoever took those pictures. The raw images don't look impressive. So all of this is very artistic and pleasing to the eye type things, which I found kind of mind-blowing at first, but when you get down to it, you're talking about statistics on a CMOS or a CCD cell. The basic idea, they collect photons, and they have little accumulators that after you say, okay, I've done exposing, how many photons have I collected, and they have a way of detecting how many of those are, and they use an accumulator. This is back down to basic electronics, I think, and those accumulators basically tell you what value that pixel should have, and whether it's a colorized filter that's sitting on top of the pixel or a black and white camera, they're all the same. They're just counting numbers and how many photons hit this sensor. And that how many photons you can this is the point I was getting around to. The photons hitting the sensor, the sensors only can handle a certain depth depending on the memory characteristics inside the chip itself. One of the important factors is they call that the pixel well, the depth of that pixel depth. However deep that well is, once it overflows, then it's just like a bucket. It starts to overflow into pixels near it. So you end up with these large blobs of white or maximized pixels, which are basically garbage. You can't do anything with them. You can't adjust levels if they're already maxed out. And one of the things I look for in my cameras was to have a very deep pixel well. And my DSO camera, for instance, it has a 65,000 pixel depth, pixel well depth. Normal planetary cameras top out around 16 to 20,000. So this has got like 3 times this the amount of pixels it can collect. So that when I collect a bunch of stuff for very long exposures, I won't max out that well. I've never done it actually on that camera. And you end up with a lot more subtlety, a lot more color variation, and it just makes for a much better camera. Of course, that camera costs $1,000, whereas the other ones are maybe around $400 or $500. So, lastly, in your final processing, you probably want to clip out all the junk that's in the photo. Like if you got an overblown star or something that was in the photo, clip that thing out. Nobody cares. And of course, framing it so it's nice and centered, all that kind of thing. If your program does it, you can create mosaics with like Photoshop or PixInsight or GIMP. And so sometimes people will have like the Veil Nebula I was talking about earlier. You can't fit that in a single frame, so people will take multiple nights or a single night, multiple frames, and then combine those at the very last. I have an example of that of the moon I did actually. And of course, after you're done, you save it to something. You save your raw image or whatever with the highest resolution and all the colors you can possibly manage. And you always make like a PNG or a JPEG that you can throw up on the web, because nobody wants a 25 gigabyte file up there. Those images are impractical to use and to move around. Of course, like everything, the final processing, all these programs have got, there's free versions and there's pay-for versions. Some of the stacking programs have some adjustments that you can use in the program itself to do the adjustment, which, I didn't put in APP. That's weird. APP has some very nice tools for doing that. But final processing, that's weird. Registax has got stuff to help you do some of this stuff, some coloration, but they tend to be relatively limp tools compared to like GIMP or Photoshop. I should also mention, if you're using Photoshop, the Pro Digital company has got some fabulous tools for taking out light pollution and some of the nasty effects that cheap lenses can do on the stars. And the plugins are like 25 and 35 a piece or something. They're criminally cheap. So why would we bother with all this? This is a lot of trouble to take a picture, it seems. The top image here is what I would say is like that's your usually like your raw or maybe your stacked image. This one, it looks like it's a stacked image of the Andromeda galaxy, a very bright galaxy. It's got lots of detail you can see fairly easily. But this is what you'll see in, say, Ypsilanti or Ann Arbor, given the light pollution. So there's a lot of background noise and this kind of fog effect, and it obscures a lot of the subtle effects in the photo, which you can see down below is the cleaned up version. So all this dimmer stuff around the outside, it basically disappears in these other photos. And dust lanes, things like that, all these little details that make your photo special disappear in this kind of mash of background noise. So that light pollution stuff, that's worthwhile of getting rid of. Those pro digital tools, they often go from this image to this image down below almost instantly. They're just miraculous. They're worth every penny. The other thing is like this image, your eye is not all that sensitive, and especially in the dark. But this is about all you'll ever see of the Andromeda galaxy. It's nearly the size of the moon, but nobody can see it because it's fairly dim. And with these cameras and these astrophotography techniques, you can pull out stuff that you would otherwise never see. Like this little object here, even the most, well, I would say some very experienced observers can see that and they know what they're looking at. But often it's just lost in the din for anybody who's beginners. So I got into it because I live in Ypsilanti and I like working off of my driveway because it's convenient. I can set up quickly and I can come in and, well, use the bathroom, get a drink, whatever. And so my observing station is relatively bad compared to dark sky sites and whatnot. And so this is a way for me to see all kinds of things in the sky that I wouldn't be able to otherwise see. So I love that aspect of it. My camera is much more sensitive than my eyeball. And with a little post-processing, which being a computer guy, I kind of like doing that stuff anyway. And it gets me images that, I can kind of stand, beat a little chest and be happy about. I mentioned before is like the stitching. This is the specs on this image. And this image, only about 2/3 of the moon you can take with that camera, as it has a very rectangular space. And this was stitched together with GIMP, which was a free program, not even a new version by the looks of it. This was taken a couple of years ago. So you can really get the details in here. I see that's a pretty brilliant image. You can zoom in forever on the thing and see as much as my telescope can see. This was taken with the 8-inch Schmidt Cassegrain. The others don't do quite as nice a job. But that's one of the things you can do, create mosaics, stitch things together. And it was remarkable. It took me about 15 minutes. It was not hard. This is just a slide I like to include because, to show other people your images. One thing you got to be careful of is, what medium. Facebook, for instance, is real easy to show off your images and put them up there, but every single one of them, they chew down the images and reduce your photo quality, which is it's a bummer. Facebook, I think, has an album feature now. At the time I did the slide, it didn't. Google Photos, it has an album feature that helps you just keep things organized, and you can notate them with extra information that will later. It's like, well, what image was this? I don't know. It's a star cluster. It looks like every other star cluster. I had a lot of stuff on Flickr for a while. Yahoo has been in the process of going out of business for over a decade, so I really don't know what they're going to do. Astrobin is fantastic, but they cost a little bit of money. I tend to do my own archival with a Blu-ray extended density disc. It holds about 90 gigabytes per disc, and any night session that usually takes about 10 to 15 gigs. So it seems to be a good medium for me. I back up everything or to the cloud, either way. And I always tell people to sign your photos, because that way you know what it was, maybe what you took it with, and who took it. Over the years, I come out with some things that I've learned along the way. If you try to use a planetary type camera, because it doesn't have that deep pixel well we talked about, they just can't image anything of the DSOs. They don't have the coolers on them. They're relatively noisy, is what it amounts to. They performance-wise, they're fine, but the resolutions, a lot of time, they don't matter. The speed of the thing doesn't matter, because if you're taking 3-minute exposures, it just doesn't care. As I said before, you can use an Alt-AZ mount, but you're going to have to deal with your exposure time problems. You'll have to fiddle with gain a little bit more, maybe use a focal reducer, which is an optical add-on. You might have to mess with a technique called binning, which combines pixels into a single pixel. Yeah, I pretty much went over the deep pixel wells. Yeah, we don't have to go over that again. The dark sky objects are often spread out a lot further than most of the telescopes can see, and most of the cameras. So sometimes you have to vary your type of telescope, i.e. your lens, so that they see a wider field of view. And that's usually an indicator of it, is what your focal ratio is. Like the Schmidt Cassegrain I have is an f10, which is relatively slow and very narrow focused. It's great for planets. It's got high resolution. It will pick up planetary detail like no other. But for picking out, say, the Andromeda Galaxy, I'll get the center core and not much else. There's a wonderful program called Stellarium, and it lets you put in your telescope characteristics and actually see what my telescope is going to see. And you can put your cameras and other stuff in there so you know exactly what's going to hit your sensor before you even go outside. Usually that's what I do my planning in. It's like, okay, I need to get it here. I need to rotate the telescope a little bit, that kind of stuff. The wider field of view, the bigger the sensor you're going to have, because you need somewhere to put all of that data as it comes in. And that's why the small focal ratio telescopes, like I think my tightest one is an F4, I believe. And it's basically a solar telescope that is turned into a dark sky. I didn't really say too much about these dark flats and bias frames, but those are the noise subtraction frames that you can take after your session. They often have to match the temperature and your optics exactly, so it's best to take them right after you get done taking your light images, they call them. I mentioned the cool DSO cameras. It's unbelievable how much noise they take out. I mentioned good tutorials on GIMP. There's books, there's a ton of websites and all that. So if you want to go the free route instead of paying for Photoshop, GIMP is a very reasonable option. I did put up a few books. These are basically, if you just want to look at the sky, know what you're seeing, even if you got a pair of binoculars or a relatively inexpensive small telescope, these will be very handy. The Cambridge and Audubon Society guides, they literally contain the night sky for all 12 months of the year, give you a nice, easy-to-read map that you can see in the dark, important. And those are great guides. They give you usually a few pages on whatever object you're looking at. They're fantastic guides. And I have both of them. I recommend both of them. But sometimes it's personal preference for which one you really like best. Another great book, if you're just trying to learn the skies, learn the constellations, is Turn Left at Orion. One of the authors, Brother Guy, he's actually a brother in the what order is it? It's escaping me now. He's in one of the religious things, but they have the Vatican Observatory. He is instrumental in their foundation. I think he doesn't run it, but he's high up in their structure for raising money for the Vatican Observatory. And I can't remember. It's not Franciscan, it's the other big one. But anyway, he's one of the co-authors on it. And that book basically walks you through how to do what they call sky hopping from one constellation to the next and to see the various sites. And it is, of course, a fraction of the material that you can actually see, but it's a really good tutorial, and it's a great book for anybody starting out in the observing. If you happen to get into astro imaging after you've spent the money on all the equipment that you don't know how to use, this is a great $43 to spend. It tells you everything you possibly could ever want to know about, and probably more, about imaging. I learned a ton from this book, and just about everybody who's experienced imagers, they all point to it as like, this is the book you should get. And the nice thing about it is it spends, the tutorials are about half in PixInsight and half in Photoshop. They show you both programs, how to do it, and what the concepts are in the programs, because the programs have their own internal ideas of how everything should work. So it's a glossy paged book, so there's tons of color photos, which they kind of need to show you all of the aspects that they're trying to show you about. It's definitely a technical read, but if you start out with that, they'll tell you the basics and move on from there. It's a great book. That's about all I have. If you got questions, I'd be happy to attempt to answer anything you got. I'm obviously I got a very broad presentation here, but hopefully somebody got something. It was remotely enjoyable instead of being told dreary.
Yeah, so I had a question.
Sure.
You're talking about the cameras. Do you know how a mirrorless would perform compared to like a DSLR?
If the mirrorless is basically, I mean, they're like the dedicated astronomy cams, because they just say, when do you want to start capture, when do you want to end. The shutterless idea is like, it's probably not going to make any difference from an astronomy standpoint, because the shutter is just a physical thing to get in the way, and will introduce some additional shakiness and motion that you may not want. So the first couple of microseconds or milliseconds of your photo might be a little blurry because of that shutter mechanism. So going shutterless it's not a bad idea. Personally, I like the astronomy cameras. Simply because the number of variables on them is a lot easier. There's a lot of stuff that you can adjust, but when it really comes down to it, it's your exposure time and your gain, which gain is kind of like ISO. It's how sensitive the sensor is going to be. It's not precisely the way, and frankly, that primer there tells you about the differences between the two. But I find like if you're talking about like a microphone if you're in a band or whatever, and you turn up the gain on the microphone, it basically expands that cone of sensitivity to include more in there. And you'll see it with a camera. You'll end up with a very bright image that may be overexposed for that matter, but you'll be able to pull in detail that maybe you can't get with just an exposure. And if you bump just the exposure, you'll get all of the background noise and light pollution as well. So there's often a happy medium between the exposure and the gain. And that's where you get really good control with an astro camera without all the complicating matters of a normal DSLR or, one of the shutterless ones. Does that answer the question, hopefully?
Yeah, thank you. FDB, it looks like you have your hand up. You can go ahead.
Okay, can you hear me?
I can.
Hi. This is Fred from Physics, Radio Amateur. I've got a C8 Celestron for sale, by the way. Anyway, separate issue. I sent you an email. But anyway.
Oh, okay.
My comment was actually, I have a former graduate student who worked for Kodak in the early days of the Webb Telescope project. And he was involved with the design, redesign, etc. And now he's finally seeing the results, although he does work for Kodak anymore. He works for a different company.
Hoover they spun off to.
Yeah, they went bankrupt, basically. Fuji put him out of business, essentially.
Right.
Long, sad story. So anyway, he was caught up in that. And they had to transfer the contract for the Webb over to another company, which he followed to some extent. But anyway, he's an expert astrophotographer, and he does really long-term exposures and stacking. He's a whiz at that, and he has generated some just amazing, breathtaking pictures with his setup, which is, I think he likes to use refractors, big refractors, expensive.
Yeah.
Anyway.
What's his name?
Tom Casey.
Tom Casey. It's not ringing a bell, but that doesn't mean anything.
Yeah.
All the photos I have here are my direct. I'm kind of in the middle of the road as far as lowbrows. We've got some guys that I know one of them. He's got some ones published in magazines and stuff. So there are some very talented folks out here. But it's a learning curve. I mean,
Yeah.
you start with really garbagey, awful images, and you work up from there. I haven't shown you some of my Drecke early ones. They look awful, but I learned so much in doing them. It's like I can't say that they're bad images.
I have another comment.
Sure.
For members of the club, maybe yourself, we have a note or a letter from Galileo in his own handwriting,
Wow.
where he shows the moons of Jupiter from an actual observation he took, and it's dated. It's over in the university library in the rare book collection. So, and you can call them and go. So I think the lowbrow should go over and see that sometime.
Yeah.
If they haven't.
We
are
are
just amazing to see in his handwriting some of his astronomy observations in his notebook. I think he was trying to get money from somebody, and this was one thing he was using, propaganda. But it was true, and it's just mind-boggling to see in his own hand this
I can imagine.
piece of paper. It's worth a lot of money, obviously, but they are happy to show it along with Kepler and other works that they have over in the rare book library at U of M. So that's a great resource for astronomy.
I know the lowbrows are. We meet in Angel Hall. We've been meeting there for years, but since they renovated the Detroit Observatory, we've been talking with them because they want to do outreach programs, all that kind of thing. It's like, well, that's kind of in our charter as well. And we're talking like it might be nice to do either some nights at the observatory or hold our regular meetings there. It would be very appropriate, but it's a matter of getting contact with the right people and all that. But the scopes and the history that they have in that place nowadays is pretty cool.
Well, try to see that manuscript by Galileo as a lowbrow night out, or maybe that would be one.
Yeah, we'll have to
think about. Okay, thank you.
Yeah.
Some other history about the Detroit Observatory and people involved. Edwin Hubble was on the short list to be the director of the Detroit Observatory.
Cool. I didn't know that.
Yeah, he was taken off because they thought he wouldn't leave his $5,000 a year salary out in California.
Well, there's that. I'm writing down these little things because our meeting is tomorrow. That might be some nice little, hey, by the way, which all of you are more than welcome to join either Zoom or come down to G115 Angel. We usually start, we gather around, like you guys, we gather around 7 o'clock, and the meeting gets started usually by 7:35. And we start out with a presenter, and then after that, we hold the business and the membership meeting for another 20 minutes, half hour or something. So if you want to jettison at that point, feel free. Tomorrow's speaker is going to be one of our own, and he's basically showing some of his shots around the thumb and around Michigan in general. And he's currently trying to write a book about all that stuff, kind of one of those coffee table type books or whatever on the sites in Michigan. And he's our wide field pro. He's done it for years. Adrian Bradley.
Okay, related to astronomy, we have pioneering radio astronomers here at U of M, including John Krause. I don't know if you're familiar with him.
Not ringing a bell, but
well,
I'm not in those circles. So.
Oops, that's astronomy also.
Yep.
And I have a talk about that. I could give some time if you want to contact me. I have my email in your.
Okay.
Notes.
Yeah, I'll look in the email, and they are always looking for speakers. I don't know if 2022 is filled yet or not, but if we have any openings or even 23, we'd be glad to have you in. We have speakers on all kinds of topics, and often there's a lot of physics stuff in there, but what the heck, we're open to just about anybody.
Well, John,
what's that?
I think you muted yourself there, Fred.
Yeah, I think so.
Yeah, Fred, you muted yourself.
Unmute. Oh, I just trying to be polite. Anyway, I was saying John Krause grew up a couple blocks from me here in Ann Arbor.
Okay.
Was a physics faculty professor, got hired away by Ohio State after he served in the Navy, and was one of the real pioneers in deep sky radio astronomy. He made the first deep sky radio map, which had all these intense objects, which later turned out to be QSOs, quasi-stellar objects. So he's a pioneer in that area, including the design of radio telescopes themselves.
Our observatory up at Peach Mountain is just down the hill from the radio observatory there, and Professor Cutler has been he got a grant for a bunch of money to refurbish that telescope, the radio telescope, get it working again, and I think they were going to do something with the Starlink satellites and some other relatively commercial satellites, but I don't know what the status of his project is, but he's pretty much the driver of that site up there. So the lowbrows are, like I say, our little squat building is down the hill, and we hold our open houses once a month, which this season looks like they're going to happen finally. So, and those are usually open to the public, and a couple times a month is what they have been scheduled in the past. So. Usually they'll have the McMath open, and then a number of club members will bring their equipment out for people to look at. So, and I can I don't know, I can get a list or something from Kim if you guys want to be in the loop. But I know you can just pay attention to the lowbrow page. They've got all their calendars and stuff online. So,
is light pollution a problem out there? I would suspect.
Well, anywhere in southeastern Michigan is a problem for light pollution, but out there it's relatively dark. It's not great, but it's not horrible. So most of the lower peninsula of Michigan is kind of in some form of green or not in the dark sky charts, which is kind of middle of the road. It's not fantastic, but it's not terrible. Ypsilanti, Detroit, yeah, it's terrible. But as you know, as this astrophotography thing and the software and whatnot, if that continues getting better, then there's no reason that you have to be geographically in someplace dark. You could be anywhere, and you can turn it into being dark pretty easily. So, and I get that's part of my tilting at the windmill action I do. I get my jollies out of, like, I did this from Ypsilanti. It's nowhere special. You can do it too. So that's part of the reason I like giving the talk. Is like, yeah, anybody can do this from anywhere. You can start out at any level and take it wherever you want it to lead you to. So my first camera was a $130 camera that I put onto the orange can there, and I got some very nice Jupiter photos. And you get to use it, you get to know what it does, and then you push out and you reach the limits of that equipment, and I say, okay, I got to get something different. And now, because I have this experience, I know what I need to get. And I tell first-time people that all the time, because, like, just buy something cheap and get started and just do it, because the process is what you need to learn. It's not the equipment. Buying nice equipment will never get you a good picture. It's all about your technique. So,
Jeff, are there any cameras that are sensitive to other than visible light?
You can get filters for just about any wavelength you like. I have a solar I have a solar telescope that has filters that'll filter out a fairly narrow band of the hydrogen alpha light that comes from the sun, and that's what gives you the solar flares and whatnot. For others, maybe you're filtering out oxygen or one of the helium elements or whatever in a particular thing, and that they usually use those as like a layer to put in. It's like, okay, I'm going to capture a whole bunch of, say, H alpha frames, and that'll bring out a lot of the red and some of the super dim stuff that you can't ever even pick up with your normal camera. And then they'll combine that in the stacking process with the other frames and get you a fuller frame that way. I don't think the cameras themselves are all that much different. I suppose when you get to the super high end, they might be, like, a Webb or something that NASA might use. But for your average Joe, and for the price of a small car, you could probably get something that will be visible light and use filters to chalk that down. That's what most of the guys that I know use, and they use it to get rid of light pollution, to enhance certain features. You can use color filters to enhance certain, like the cloud layers of Jupiter. People usually use a number of different filters on those to bring out the fairly, different characteristics of the cloud layer that may not show up as well if you use straight visual white light. So I haven't really gotten into the filter thing real deep. Just trying to get my bearings, get my procedures down for the normal stuff, and then we talk about filter wheels and that stuff.
Okay, thank you.
Mm-hmm.
I saw FTB's comment on that too.
Yeah, I have a Lunt telescope for. Can I get out of here? Probably. There we go. And you can see the wealth of albums. So this is my solar telescope setup. It's a Lunt modular, so that like this white piece, this red piece, and then the diagonal here are all specific to the H alpha region of the wavelengths for H alpha. It's not what I'm thinking, the word I'm thinking of, and it's modular because you can actually take those pieces out and get yourself a short tube refractor. But those are, you can see this, you sort of see this big black knob up here, and that's what adjusts the, there's a pressure, it's called pressure tuning, and I can't tell you what's inside of the thing, but higher pressure changes whatever optics that they have to squeeze it down to a certain wavelength, and you can adjust that, and it's never the same adjustment for the sun, because the sun, depending on where it is, where the flare is coming up on that disk, it may be closer or further away, so there's always some fiddling you got to do with it. This one on the end here is a secondary one that you can do additional filtering on, and this is my planetary camera, which looks like yet another hockey puck. Red hockey puck, but these are the kind of, this is the view you'll get through the eyepiece. This was actually taken with a cell phone through the eyepiece of that telescope, and so you can see where it's picking up the sunspots, which in visual light, these are black, they're dark regions, they don't appear that way, but it picked up these flares, some of the loops, the prominences and filaments as they're called. And of course you capture and then you process them down to see what you can get. And I was just getting my my bearings on this particular scope. The other telescopes are in here, I think. That's the Lunt. Yeah, this is the other setup. It's my 120 millimeter refractor. This is the $250 telescope. Put on a $1,000 mount with a $1,000 camera. But I was playing with a different focuser control. So usually focuser controls are essential when you're doing the dark sky stuff. Things are just too small. And when you get into the automated programs, they actually have programs that'll take a frame and see if it's in focus, take a second frame and change the focus, and then basically hone in on a perfect focus, so that you don't have to worry about any of that, but it requires a motorized focuser. And then the final setup, well, yeah, some of these are remote controlling. Long cables work. That's a good picture of that. That's the orange can. This has a finer scale focuser in there, and then the DSO camera, which you can see the cooling fins here. There's a fan that runs on it and off of 12 volt power, and it cools down the telescope. But you see already we got dew and frost forming on the outside of the thing. So, and all this is from my driveway in Ypsilanti. So that's the typical setup. You got a small camping table, your laptop, and you plug it into a bunch of stuff.
An interesting comment.
Did you look at the last eclipse in 2017? Planning to look at the next one, 2024?
I am planning to look on the 2024. I think it's in April 8th or something like that.
Yeah, Carbondale, Illinois is the best penumbra you'll get. Yeah. I was there for the 2017 event.
Yeah, this is the first DSO that I took, and you can see this is the Orion Nebula, and it doesn't look anything like what I had before. So you kind of learn along the way, and I think some of the planetary ones are pretty cool too. This one I caught the moon there, and this one's kind of special because I think this was it's not Io. Begins with a G. I'm having mental flatulation, but it was
Ganymede?
it was Ganymede. Thank you. It was positioned so that the sunlight was coming this way, and it cast a shadow on the planet's surface there, or the atmosphere anyway. Which I was tickled pink to catch that. Which I don't know. Did that show up on your screens there?
Yes.
Good.
I had a comment about sunspots.
Yeah.
So we have a solar telescope over in physics we use in our high school summer program.
Okay.
The advantage of solar observing is you don't have the light pollution problem, and it's nice and warm.
Yeah, sometimes that warmth gets in the way too, because your things get hot.
But you know who was one of the first to observe sunspots? Galileo, of course. And interesting story is, originally it was conjectured that these sunspots might be images of a planet going across the sun. And that planet, for Star Trek fans, is called Vulcan. But then after more observations, of course, it was a small planet near the sun was ruled out.
One of the
Mercury.
One of the problems in photographing the sun is you end up with a lot of heat related issues, so focusing is often a big hassle. And in this photo here, this actually shows I had 2 dust donuts. There's 2 pieces of dust on the sensor itself, and that's the way they appear. You don't notice these things until after you've done them for a while. It was like, hey, look at that. So you're keeping the darn things clean in the interim. That was
And of course, as radio people, we pray for sunspots. That's interesting.
These images here, this is the eclipse that we saw. It was in North Carolina, and it started to rain. This is the cloud. It was the only cloud in North Carolina, and it came directly over us. And that was during the eclipse, and it started to rain. And I basically took pictures as to how dark it got, as things went on. It was terribly depressing. I told friends later, it's like, yeah, we got rained out in North Carolina. I was like, what are you talking about? I was in North Carolina. It was beautiful. Like, well, that one cloud? Well, it's right overhead. I think I've shown you guys all that stuff. Anyway, any other questions? I got my captive audience here.
I think I had a quick question. So if you're trying to do very long exposures for very deep space objects, is there any advantage to having like a film camera over a digital camera?
I don't think so at this point, because the digital cameras have gotten so good and they're so adjustable. I would think that the big disadvantage with the film camera is that you're not going to be sure what you're going to get until you develop it. And, developing and all that, there's variables that can creep into it there. The nice thing about a digital camera, of whether it's a DSLR or a dedicated astronomy camera, is that both of them, you'll be able to take test shots. And like a lot of times, my session begins like, well, I got to get this thing so I can at least see the object first, and then we'll dial it back or forward as necessary, depending on what I'm shooting for. And that ability to kind of, I need to take some scrap photos first, that tends to be very handy. Now, as I become more experienced, I don't do as many of those. So I don't think film has any advantages anymore. And frankly, some of the different film types are becoming harder and harder to come by. And I have heard that Fujifilm has got a green tint to it overall, whatever their substrate is. So that's something you have to work out later in post. I mean, well, I guess there's not much post-processing.
The post-processing for a film would be very different than
Yeah,
just digital.
yeah, and that's where that deep sky imaging, the book there is they kind of start out with us like, well, this is the way it used to be. We don't do that anymore. This is the way it works, and frankly, there's so many more options. I mean, unless you're a hardcore film addict, I can't see why you'd want to go through the trouble. I just one of those shruggy points. I honestly don't know why people use the DLSRs over a dedicated camera, because I found it so easy to take really spectacular pictures with the dedicated cameras. It's like, why would you mess around with anything else? I mean, all the stuff I showed you tonight, with a couple of exceptions, that's all came in on my work, and I'm not an expert at this. I can show you pictures that'll blow your hair back from the lowbrow guys that they're good at, and they're not even the experts in their field. So it's all like any hobby. It's as much as you practice and get used to your tools, and the more familiar you are with the process, the better your results are going to be. And it's a journey. It's not there's no end to it. It's worse than music.
That kind of makes sense, though.
It's like anything you have to become an expert at. There's a learning curve, and you really never stop learning. So the little camera that I started out with, this guy here, it's literally a $130 camera. They don't even sell it anymore because they improved it. Version 2 is so much better. They don't bother with the old one anymore. And this has actually got a fisheye lens, so if you want to take wide sky photos with it, you can do that. I actually loaned out my old camera to a kid in Dexter that was just starting out. It's like, I don't care, I don't use it. But it could have been used if it had continued working. It turns out the age of the thing was old enough where it doesn't work with the newer USB 3 protocols very well. It was USB 2 only, and it was a funky variation of USB 2 that it doesn't play well with others. But if it's the only camera in the stack, it'll work fine. But I was going to use it as a guide camera, and I just couldn't hold the setup together. And now the guide camera I have is this nice little compact thing, and monochrome. But the other thing that I really didn't mention too is there's the control systems. I use right now. I'm trying to get used to using. It's based on a Raspberry Pi, and there's a load that's a free load called Astroberry. There it is. And this is the Raspberry Pi, and I just mounted all my power supplies and the USB hub and stuff into it. I use a 512 gigabyte removable storage, so at the end of the night, I just unmount that thing and plug it in my Windows laptop, which has got all the processing software on it, and go to town. But this little guy has got enough to do all the capturing, all the automated the planning work and whatnot that I mentioned before. It pretty much does everything. The package, the load comes with all that software loaded, so you basically use a program on your PC or Mac to burn the card, put the card in, boot it up, and you're done. So it's pretty painless. This package they give that is called K-Stars, and it comes with a sub package called Echos with a K. Swedes. But it does everything, and it's a fairly competent package. So, but that's what I use this, and I just hang it from the tripod. It's got a single plug that goes off, and I've tested it with a battery, one of the new lithium battery packs, and it says that if I don't plug in my laptop, I probably will get some 20 hours out of the battery, and that's at room temperature. That's not regular, and well, that's the refractor with the. It's got a new guide scope and guide camera on it, and the automated focuser and whatnot, which I added. So there's more money in all the pieces parts I'm gluing onto this $250 refractor, but that was what took that nice image of the Orion Nebula, which again surprised the lowbrow guys, because it's like, what? Yep. So they have fun with it. I think those are all the good. Trying to dig up if there's any images I didn't include, but I think I got the best of the highlights there. But yeah, that Orion image was special. I guess the only other thing I have to really show in this area is the Eagle Nebula. This picture, there's if I can get it to zoom. I can't. There, these three cloud structures here are known as the pillars of creation, and they usually are fairly subtle, but I managed to pick this up, and this was with that Alt-AZ mount. So I did a double on this one. I managed to pick these things up with a telescope that wasn't supposed to be able to pick up this kind of object, using a mount that was supposed to be incapable of doing good images. And you can see the stars here are relatively round. There's only a few that are smeared out toward the edges, which that type of telescope has that characteristic. But overall, catching these things, that was just like, wow, I can't believe I did it. But, you know, experience. This is probably the last deep sky image I took with the orange can before I got that the cheap refractor. The cold can is what I'm referring to it. But yeah, I think you've seen all the rest of these. This one is a little redder because a friend did some processing, but this also shows this vignetting, this circle. That's common in the SCTs, so that's why they don't use them for the deep space stuff as much. Although a lot of this is cloud that you wouldn't have otherwise seen. But this blue halos around all these stars, that's the cheap glass in the $250 refractor. It's $250 for a reason, but to get rid of that is going to cost me about $3,000. So I thought I could probably make do in Photoshop and get rid of it. Oh yeah, post-process, Brian Autumn. Brian Autumn actually is, he's a doctor, and he actually does astrophotography for money. He's a professional. But he took it. He's one of the lowbrow friends that we've made. So, anything else while we're here? I can't believe I've talked for an hour and a half. Or at least a good hour. Oh. Caught the Horsehead Nebula there. Didn't even realize that. Stuff you find when you're not looking for it.
Well,
Anything
looks
else?
yeah.
It was a really great talk.
Yeah, it was really awesome.
I'm glad you enjoyed it. You can tell that I sort of like to talk a little bit about this stuff. And if anybody's ever passionate about any topic it might be, it's like, give a talk on it, because you'll inspire somebody else. It always turns out that way. So
It makes me want to drag my mighty ETX out again.
hey, that's a good scope. That's got good glass in it, and the mount is pretty solid. You could hook a camera up to it real easy. And like I say, one of the ZWO line, they've got some for a couple $100 that would just do marvelous wonders on it.
Yeah.
How about a Meade scope? That's what I got. Will it work?
Yeah. If it's got a telescope with a 1/4-inch adapter, you're golden. I mean, my that big red can with the cooler on it, that has a 1/4-inch adapter on it, or you can run 2-inch. It's your choice, and they run equally well. So you could plop that on there. There's always balancing issues. So like the ETX, you probably have to stay with a smaller camera, just because it's probably not that adjustable for the balance. I have a rather embarrassing photo that maybe I'll just finish things out with it if I can dig it up quickly. I had trouble with the balance on my SCT on this new mount, and I ended up needing more weight on the one end, and where is it? I know I've got it. I ended up finding some extra weight. I had an extra weight that was made for a different area of the telescope, and I ended up plopping it on there just to balance everything. Maybe it wasn't on the SCT. Nope. Yeah, it was duct tape and a weight. It was just embarrassing. And I'm not going to find it because I'm looking for it. You know, as soon as I sign off, it's going to appear in front of my nose. No, it's got to be somewhere else. Oh, crud. Anyway, it was on this new mount that I got, the equatorial mount.
Look at what Dave's holding up.
Oh, nice.
That's the mighty ETX.
Yeah, and that looks like one of the bigger models too. That's like the what, a 150 or something?
Yeah,
It's not the 90 millimeter.
no, this is the 125.
125. Okay.
Yeah.
Does it look like it was the bigger? That's the Maksutov.
Well, make it look big like this in the camera.
Well, there's always a little bit of that. Where the heck did I put that? Yeah. Well, anyway, don't use duct tape and weightlifting weights. They don't stay put. It was a nightmare. Huh. That's funny. Wonder where I put that. Normally, I keep the albums of just the photos, and the miscellaneous is where everything else goes. But oh well.
Yeah, I did get the adapter for it to adapt it to the laptop so Solarium can drive it.
Yep. Sky Safari, Stellarium.
Yeah.
And then there's I think Starry Night, I think, is the other one, and they can run on a cell phone, and sometimes they even have adapters for Wi-Fi. And like this AZ Pro mount that I have, it had built-in Wi-Fi, so you could talk to it with Sky Safari and use your phone to guide it. It turns out it interfered with my home wireless, interfered with the wireless it was trying to broadcast, but that issue aside, it actually worked really well once it was out of range. So, and you'll notice we have a few cats around, so downside of astronomy talks, they see the cats. So, anywho, it has been a pleasure. I say I invite anybody who wants to come to the Lowbrows meeting, either Zoom or stop in at G115 tomorrow evening. We usually gather around 7 and things get going around 7:30. It's very much an open house and open to the public, so if you're all interested, come on in.
Yeah, thank you again for taking the time to speak to us. It was
Sure, my pleasure.
As you both said, very informative.
Oh, I hope so. That's the idea anyway. Stop share. There we go.
All right. Well, I guess thank you all for being here for our last meeting of the school year. Hopefully we'll see you next September, or this September, I guess. Since you're here,